Hi everyone. Sorry I'm a little bit late. As I was in an important call, so I kind of messed with our house and our roof that I have to deal with. So welcome to our eighth recitation. The bulk of the slides are on proving properties of relations, but I also want to go over some notes that I have for quiz 2 and make a couple of announcements. Solve two set problems that will appear in quiz 3. And then take it from there. Okay, so in the previous presentation, I posted the breakup of the scores for quiz 2. I don't have it in this version of slides, but it's a little bit worse than quiz 1, but it actually doesn't look that bad. For example, almost 20% of students scored above 95 points on quiz 2. And more than half of the class scored above 80. So those are pretty decent scores for, I would say, what is probably going to be the hardest quiz of this semester. And then a couple of announcements. So our quiz 3 is next week, October 20th. And the same as before, it's a 1 hour window between 7:30 and 4. So you know the drill. You have 1 hour, then half an hour to submit it and so on. I'll say it again, use this half an hour grace period smartly, because we don't accept quizzes submitted through email anymore. You have to submit through Gradescope. So quiz 3 will be on sets and Boolean algebra, which is chapter 3 in your textbooks, or lectures 8, 9, and 10. Of course, there will be questions about doing element-wise proofs about sets. And so make sure that you also know proof techniques from chapter 2, because it kind of builds on top of that. We also released homework 4, so you can start working on it. And then due to several requests for this, in particular for you to see quiz solutions, going forward, we will be solving, let's say, hardest quiz problems that you struggle the most during discussions after the quiz. So on Thursday, TAs will solve a couple of challenging quiz 2 problems during discussion sessions. We'll also post some solutions on Piazza as well, so you'll have access to these. One more thing I want to say and comment a little bit before I ask about if you have any questions is that know that we have 4 recitations and 4 discussions, right, on Tuesdays and Thursdays. They're not exact copies of each other. So even when I do 2 recitations in a row, depending on the number of questions, they might be slightly different. I might cover things slightly differently. I might solve some additional questions in one recitations and so on. And the same thing goes between me and Professor Phillips. I think in general, she actually manages to solve more questions during recitations than I do. So she's a little bit faster. I do breakout rooms and so on. I'm a little bit slower. So you can pick and choose your recitations based on the style you like. And also they're all recorded and available on YouTube for you to watch afterwards. So you can kind of go through them quickly afterwards to see if there are things that were maybe covered in our recitations and not in this one. Okay, so these are the announcements I had. Any questions about these? Okay, so let's then for two problems, relatively easy problems on sets. So here's the first one. I'll give you 1 minute to solve it. We have 2 sets A and B. They're a little bit interesting because some of their elements are sets themselves. And you have to write out the result of this Cartesian product operation that multiplies A and B. So try to do this, and then I'll do it for you. and I'll give you 1 minute. Okay, so let's do this. So Cartesian product is a set. It's a set of pairs of all possible pairs of elements between these two sets. So we have A1, we have A comma set 2, 3. We have B comma 1, and we have B comma 2, 3. So that's the solution. So there's a solution. One thing to be a little bit careful about is that A times B is not in general going to be equal to B times A. So the order does matter. So if I ask for B times A, basically the order in these pairs would be the opposite one. Any questions about this problem? By the way, right now we usually hover at around 30 students who join these recitations, which is, way less than kind of 50, 60 that we have initially. So, so if you want to ask a question, and you are more than welcome to just unmute yourself and, start asking your question. It's not going to cause any kind of confusion or anything like that, because there isn't that many of you. So that's another way to ask questions, apart from writing them in the chat. Okay, let's move along. So I'll do this simple proof. So it's a proof about sets. We want to prove that any set A is a subset of itself. And this is actually, it's a very simple proof. When you look at it, it almost doesn't look like a proof, but it is. So let's first see how we define a subset. So if for all x element of A implies that x is an element of B, then A is a subset of B. So that's how we define subset. Now, it trivially holds that for all x, if x is an element of A, that implies that x is also an element of A. That's clearly holds. And because of that, A is a subset of A. And so this concludes this proof. So like I said, it's such a simple proof that it almost doesn't look like a proof, but this does it. So any questions about this proof? Okay. Okay. Let's now move to relations, which is what we were doing in the last couple of lectures. So just a reminder of all the different properties that we talked about that you can define for relations. So if you have a binary relation R on set A, then it is reflexive if A comma A is element of R for all A's element of A. So if you remember from the lectures, when you're looking whether a relation is reflexive, you're looking for these little loops around every element. So it's irreflexive if and only if A comma A is not the element of R for all A's. So that's, here is an example of a relation that is irreflexive. So note that the relation can be neither reflexive nor irreflexive. So in this relation on the right, if I add a little loop on one of the elements, now this relation is neither reflexive nor irreflexive. Okay, then it's symmetric if AB element of R implies BA element of R. So we are looking for things like this. Antisymmetric if you don't have such back edges. And transitive if AB is an element of R and BC is an element of R, then AC has to be an element of R as well. So this will be a small example of a transitive relation. And then we defined a bunch of different kinds of orders. So it's a partial order if it's antisymmetric, transitive, and reflexive, or RAT. Strict partial order if it's antisymmetric, transitive, and irreflexive. Then a total order if it's a partial order and also every pair of distinct elements are comparable. And strict total order, the same except it's irreflexive. So those are the different kinds of orders that we talked about. You don't have to know these by heart. You can write them down in your index card so that you have a good reminder during the quiz. Excuse me. Okay. So I see there is maybe a question. Can sets be both symmetric and unsymmetric? That's the question. So, okay, first of all, these are properties of relations and not sets. However, we can specify a relation using a set. So they cannot be, they can be neither symmetric nor antisymmetric, but they cannot be both symmetric and antisymmetric.
So does the symmetry count when it's an element referring to itself, or is that?
I see what you mean. I have to check this. I believe it does, but I have to check this.
I think there was a question on the quiz last night where there was a set that was kind of similar to that with 1, 1, 2, 2, and 3, 3.
Okay.
I believe the correct answers were that it was symmetric and antisymmetric.
Okay. So let me double check this. I need a pen. Where's my pen? It is somewhere here on the table. That's a good question. I will check this and I'll post the answer on Canvas or on Piazza.
Okay.
I can't find the pen now. It's funny, I just had it like 10 minutes ago. I can't find it now. I definitely know that it cannot be both reflexive and irreflexive. And I'll check this one.
Can you give an example really quick of one that could be reflexive, can be neither reflexive or irreflexive?
Yeah, it's pretty easy. Let me go back. So it's this one that I already showed. So this one. So you're looking for a relation that, has this little loop on some elements, but not all of them. So now, if you look at reflexive property, it needs to have this loop on all of the elements. So it's not reflexive. And irreflexive, there shouldn't be a loop on any of the elements. So it's not irreflexive either. So that's an example of a relation that is neither reflexive nor irreflexive.
Thank you so much.
Okay, any other questions? Okay, so let's move along. We talked about orders. And then another property of relations that we talked about, it's our equivalence relations. So a rationalist equivalence relation if it's reflexive, symmetric, and transitive. So R, S, T. And I always have to look these things up. So I do suggest that you, write this down on your index card so you don't forget about it. Okay, so let's first do kind of a simpler question, and then we'll do 2 questions that involve proofs. They're actually not that hard, but definitely harder than this. So let's see what we have here. Okay, so set partition. We covered these in the last 2 lectures as well. So a partition of a set is also a set. It's a set of sets such that each of these sets is a subset of the original set. They are not overlapping. So if you take any 2, the intersection is an empty set. And their union is the original set. So that's a set partition. And equivalence relations can induce set partitions. So if we have this set A, which contains integers from 0 to 6, and we have this relation R on this set that is defined as a set of pairs x, y, such that x minus y is divisible by 3, then what is the partition of A induced by this relation? So this partition is going to be a set, and it's going to contain a couple of subsets of A here. And all elements of each subset have to belong to R. So no matter how you create pairs within each subset, each pair has to belong to R. So I'll give you a minute and try to write down this partition. And then I'll solve it for you guys as well. Okay. So let me do this. So let's start. Okay, 0. Who does it belong to? Belong with? 0, 3, 6. You know, 0 minus 3 is divisible by 3. 0 minus 6 is divisible by 3. 3 minus 6 divisible by 3. 6 minus 3 is divisible by 3. So no matter how you pair them up, the pair is always divisible by 3. Okay. Then 1 goes with 4. One minus 4 is divisible by 3. 4 minus 1 is divisible by 3. And then 2 goes with 5. So that's the partition that is induced by this equivalence relation R. Any questions about this?
Hi.
Yes.
So can I just write like the 0 and 3 is the pair, and I roll like 0, 6 is a pair? Is that correct?
So you want to do
Like I
0,
said,
3
the
or
first,
6 standing on its own?
yes, I roll like 0, 3 is the first pair, and 0, 6 is the second pair. Is that still the same result as yours?
You wrote 0, 3,
Yes, and 0, 6.
0, 6, like this.
Yes, and the rest is the same like yours.
Yeah, so that's a good question. So if you remember, so all sets in the partition, their intersection has to be an empty set. So any pair of sets belonging to a partition, the intersection of this pair has to be an empty set. And in your case, if you intersect 0, 3 and 0, 6, it's not empty. The intersection is 0, this set containing 0. So this would not be a partition, and
Yeah.
therefore it wouldn't be a correct answer.
Okay, thank you.
Okay. Okay. Great. So let's move along. Let me just cross this. This would not be good. Let's get to, let's say, more challenging ones. So I have two of these questions. They're very similar. Typically, they follow the same structure. So I'll do the first one, and then we'll do breakout rooms for the second one, where you guys can do it on your own, and then we'll look at the solution together. Okay, so we have this relation R over integers, which is defined as a set of pairs A, B, where A minus B has to be even, and we're going to prove that it's reflexive, transitive, but not a partial order. So let's talk about not the partial order part just a little bit first. So if you remember, partial order, it has to be rat. So it has to be reflexive, transitive, and anti-symmetric. So if we want to show that it's not a partial order, we have to show that it's not anti-symmetric. And I'll show how to do that. Okay, so let's first do reflexive and transitive proofs. So let's do reflexive. So if you remember from the lectures, the structure of the proofs, the skeleton of the proof, of all these proofs is always the same. We start with assumptions, and using a direct proof, we want to derive the conclusions. So in the case of reflexive, we have some A that is an element of Z. And from there, we want to derive that A comma A is an element of R. And we have to fill in the middle here. So how do we do this? Well, if A is an element of Z, then we know that A minus A is equal to 0. And that is equal to 0 times 2. So basically 0 is even. And that means that A comma A is an element of R. So that finishes our reflexive proof. So proofs that a relation is reflexive are typically very straightforward. Okay, so that's reflexive. Now we want to prove that it's transitive. So let's do that here. So what is the structure here? We have let A be an element of R and BC is an element of R. And we have to show, this gives us a hint, right, of the structure. We have to show then AC is an element of R. Oh, we have to fill in the middle here, right? So if AB is an element of R, then we know from the definition of R that A minus B is equal to 2 times some K, where K is an element of Z. That follows just from the definition of even. Let me erase this to free up some space. Okay. If BC is in R, then we know that B minus C is equal to 2 times L, where L is an element of Z. Okay, now if we add these two equations, B's are going to cancel. And we are going to get A minus C is equal to 2 times K plus 2 times L. That is equal to 2 times K plus L. And now, because integers are closed under addition, closure of plus, sorry, let me just fix this. We can introduce a substitution. So that's equal to 2 times M when M is element of Z. And therefore, A minus C is even, and therefore A comma C is an element of R. So that proves that it's transitive. And finally, if you remember from the previous slide, we want to show that it's not antisymmetric. So we want to show that there are two elements. Well, there are two pairs. Okay, so well, how to show that it's not antisymmetric? So for that, you don't need a proof. You just need one counterexample showing why it's not antisymmetric. And you can find many such counterexamples here. A simple one that I found are these two pairs, 4, 2 and 2, 4. So both of these pairs belong to R. 4 minus 2 is even, and 2 minus 4 is even. And 2 is clearly not equal to 4. So if you remember from the definition of antisymmetric, if you have AB that belongs to R and BA that belongs to R, that can happen only if A is equal to B. So here I have an example where that is happening and A is not equal to B. And so this is a counterexample, and it shows that it's not antisymmetric. and therefore it's not partial order. So that solves this problem. So I have another kind of similar proof that I would like you guys to do on your own. But before we go there, any questions about this one? Okay, great. So here is another relation, similar to the previous one. It's over integers as well, but it's defined as a squared minus b squared has to be equal to 3 times m. And we want to prove that this is an equivalence relation. So you want to prove that it's R, S, T. You want to prove that it's reflexive, symmetric, and transitive. So let's do maybe breakout rooms for 6-7 minutes to give you a chance to do this on your own. So feel free to discuss it in the breakout rooms, and then we'll come back and I'll show you with you guys and we'll go over it. So see you in a few minutes. Enjoy your breakout rooms.
So my group is already done, or at least I got through it, and I think they understood it. But I have a question on the regrade policy.
Go ahead. Yeah.
So for quiz or for test 2, I got like 3 out of 20 on question 6, but I believe that my proof was correct. Like it showed that it proved it, but I don't think I used like I know I didn't use like the proof definitions, I guess. So like proof by closure, I probably didn't
Yeah.
write that
Okay.
down. Is it
So-
possible that I could get a regrade and I guess I just want to know how to do better on future tests more than anything. So just make
Yeah.
sure to write those little principles, or what's the best way?
So could you message me separately, just kind of on Piazza or somewhere, or send me an email?
Sure.
You have to ask for a regrade through GradeScope within 1 week after you got your grade. I think we at this point released the grades more than, I forgot when did we release them.
It was last week sometime, so I might be too late. I thought it was like Tuesday.
Maybe you're just late by a day. Anyways, send me an email. And in general, I can take a look and I can let you know what went wrong.
Awesome, thank you.
Let's take this offline. But good, yeah. Thanks for asking, and just message me right away.
All right, will do.
Yeah. Okay. Okay. Welcome back, everyone. I hope this was fun. I hope you managed to solve it. Let me just quickly go over it. I'll go faster than last time. So reflexive, that's the first one. What do we have? Let A element of Z. So that's the same as last time. So then we know that A squared minus A squared is equal to 0, which is equal to 3 times some 0. From there, we know that A comma A is an element of R. So that proves reflexive. Next one we need symmetric. So let AB be an element of Z. Oh, sorry, element of R. So that from the division of R, we know that then A squared minus B squared is equal to 3 times M. If we multiply both sides by -1, we get that B squared minus A squared is equal to 3 times M times -1. And that is equal to, because of closure of multiplication, that is equal to 3 times N, where N is an element of Z. And therefore, from the addition of R, it follows that B comma A is an element of R. Great. So that solves the symmetric part. And the last one we have to show that it's transitive. So now we have let A be element of R and BC an element of R. And we have to show that AC is also an element of R. So it's if AB is an element of R from the definition of R, we know that A squared minus B squared is equal to 3 times M, where M is an element of Z. And we have the similar thing from BC. So we know that B squared minus C squared is equal to 3 times N. Oops. I made an important mistake here. You cannot use the same variable, right? They're not necessarily the same number, right? So you have to use M and something else. N, where N is an element of Z. Similar to the rule before, if we add this up, B's cancel, and you get A squared minus C squared is equal to 3 times M minus 3N. That is equal to 3 times M minus N. And now we have closure of subtraction. That is equal to 3 times Mn, let's say K, where K is an element of Z. And therefore, A comma C is an element of R. Okay, so that that does it. So we showed that it's reflexive, symmetric, and transitive, and therefore it's equivalence relation. Any questions about this this proof?
So I was kind of wondering on the symmetric one, where did you get the -1 from?
Good question. Okay. So here, I multiplied both sides of the equation with -1. So, you know, if you have an equation and you multiply both sides with the same number, the equation remains the same. And so I multiply both sides with 1. And then if you multiply the left-hand side with -1. And so if you multiply the left-hand side with -1, you get B squared minus I squared. And if you multiply 3M with -1, you get 3 times N times -1. So I hope that answers it. And why did I multiply with -1? Well, you know, I know what my goal is. You can even write it down as a hint. So I wanted to derive that B comma A is an element of R. And if I look at the definition of R, I know that I have to get something like B squared minus A squared somewhere to be able to derive this. And so I looked at this and I was like, oh, I'm not quite there. I have to somehow flip them. How do I flip them? Well, I flip them if I multiply it with -1. So that's why I did it.
Okay, that makes sense. Thank you.
Yeah.
What exactly does Z squared mean in the relation in the problem itself?
Good question. So it's a shorthand for Z Cartesian product with Z.
Okay, cool. That's what I thought. I was just making sure.
Yeah, no, it's a good question. I think we use this in the lectures as well, but if we did not, it's a shorthand for Z Cartesian product with Z.
Thank you.
Any other questions? Okay, so if not, I'll actually stop here in the interest of time because Bay has to join the Zoom meeting. So I'll post notes. As I was mentioning, I'm usually slower than Professor Phillips, so there are a couple of other questions that I didn't get to. I will post their solutions in our scribbles, so you can look them up there, and she might get further than me. So, but that's it. That's it for today. Thank you all for joining.
Thanks.